All right. So welcome everyone. So today we're doing a webinar. So Telops is presenting its new improved algorithm for the detection of gas with our hyperspectral instruments. So I'm Antoine Dumont, Field Application Engineer at Telops. I'll be joined by Martin Larivière-Bastien, who is a Senior System Designer at Telops, really a pillar in the development of hyperspectral instrument and analysis at Telops. So I'll just do a brief outline of our webinar. So I'll introduce Telops for those of you who are not familiar with Telops, including our product line, especially our hyperspectral products, and discuss a little bit the basics of the hyperspectral imaging before we get into our main topic, which is the improvements on the algorithm for the detection and identification of gases. So we'll talk about the changes that Martin basically put into the new algorithm. Sorry, there's a new method to talk about how that algorithm was important for the improvement. So we'll talk about the ROC curves. We'll have a few examples of false alarm suppressions with some ground and airborne campaigns as well. And we'll complete the webinar with some questions and answer. Before we fully get started, we always like to give a little poll to see the level of experience that our audience has with the topic. So let me just launch this. So you should be able to see the poll. So you can just click on the answer that best represents you. So how would you rate your knowledge of hyperspectral imaging technology? So either no direct experience but interested, no experience but you've considered the technology, you have had experience before, or you consider yourself an actual hyperspectral imaging expert. So I'll give maybe 30 seconds to collect some answers. Okay. So this is the result, a very interesting result. We basically have an interesting spread of people in our audience, some without direct experience, quite a few that do consider themselves experts. So that's great. We're hoping that those improvements in the algorithm will be interesting to you, the people that do have direct experience as well. So I'm hoping for some great interactions and great questions at the end of the webinar, and hopefully you'll find this quite interesting. Okay. So a quick note about Telops. Telops was started in 2000, so we'll be celebrating our 25th anniversary next year. So we started in Quebec City, and we're still there nowadays. We employ over 90 people with different advanced degrees. We have established ourselves over the years as really world leader in thermal infrared imaging solutions, and we're quite proud of that. And we're really pushing innovation of products and technology and different kinds of analysis in that field, especially in hyperspectral imaging. We especially have a new innovative solution, so a new service for aerial methane leak detection and quantification. So it's a really important field nowadays to detect the emission of leaks of methane for, in particular, the gas and oil industry. In the last year, Telops became part of the Exosens group. So Exosens basically aims to cover the whole electromagnetic spectrum, as their logo describes, or reveal the invisible. And that really allows Telops to expand that innovation and figure out ways to push that innovation and that technology as much as we can. So we're quite excited to see what will come over the next few years with that new acquisition. So the Telops products, we have a broad range of different cameras and systems. Today, of course, we'll be talking mainly about the hyperspectral cameras that we see on the left. There's my pointer. So the hyperspectral cameras, I'll talk about those a bit more in detail in the next slide. But we have a whole range of broadband infrared cameras from shortwave, midwave, and long wave range as well. And in the in-between systems, I would say, between broadband cameras and hyperspectral cameras, we do have multispectral systems, which are, the core is a broadband IR cameras, but we have a filter wheel in front that allows 8 filters to acquire that infrared scene so simultaneously. So have a filter wheel spinning very, very fast. And so you have a little bit of spectral resolution if you want with those filters, which is very interesting. You can distinguish between different types of gases when using that type of instrument. Of course, it's nothing compared to the spectral resolution that we have with the hyperspectral systems. So talking about those, we have on the left our HyperCam legacy system. This is the hyperspectral system that has been at the foundation of Telops innovation with this technology. It's still a very powerful system that can give extremely high quality data, even though it's older compared to the other system and a bit more robust, a bit heavier, of course. The core of it is still extremely powerful. But over the last few years, we've developed some new instruments. So we have the Airborne Mini and HyperCam Mini XLW, both systems in the long wave spectral region. They are basically a miniaturization of the original systems. They offer the same capabilities, but for the airborne, this was established, installed on a stabilization platform, which offer a really interesting option, flexibility to do those measurements from the air. And the HyperCam Mini XLW is a much lighter unit that basically only one person can use by themselves in the field or in the lab, and is much, much easier to use. So today, the goal is to talk about gas detection. I just want to give a quick glance into the various type of applications that we have here at Telops that touch all our cameras or our systems. For the hyperspectral systems, gas detection is the big one, of course. But if you have those kind of hyperspectral systems, you can do IR signature identification, not only on gas, but also on solid surfaces, particularly for mineral identification. This is a growing field as well that uses hyperspectral imagery just as well. So if we're to dig into the hyperspectral technology a little bit more, there are different systems out there using different methods to achieve hyperspectral imaging. The Telops cameras do use FTIR technology, so Fourier transform infrared. So that means that as a maybe simple diagram for the core of the system here, we have an interferometer. So we have a fixed mirror and moving mirror inside the hyperspectral camera. So the moving mirror displaces, and the radiation from the scene recombines towards the detector, and that creates destructive and constructive interference. So on every pixel, it results as an interferogram. So that interferogram that you can see while using the system is put through a fast Fourier transform. So that fast Fourier transform is what basically converts that interferogram into a spectrum that you can be used to do some chemical analysis to understand what kind of compound you have within your scene. So since you have that for every pixel in your frame, that's why we call the data that we obtain with this kind of system a hypercube. We call it a cube because we have the standard X and Y direction that we have with any kind of image, visible or infrared. But in the Z direction, we have that chemical spectrum, that spectrum analysis that you have in a wave number or wavelength, that basically creates that three-dimensional data set. So with that spectrum information, you can get all the information you need, either in absorption or emission characteristic, to determine what kind of material or gas you have at your target. So with this kind of system, this kind of technology, it has quite a few benefits. You have quite a fast data collection. You can have up to several frames per second. You have quite a high specificity for that detection and identification of compounds. You can detect and even quantify multiple gases, such as methane. We have NO2 and 2O, SO2, volatile organic compounds, and Believe me, plenty more. Not only gases, but like I mentioned, you can do that for solid materials just as well. There's a bit of a caveat with solid materials. We're not talking about identification through a lot of solid material. It's only a surface analysis in that case, of course. And there's a little bit of post-processing that needs to be done to properly identify those kind of targets. So we have a classic kind of gas detection here. Those of you who have looked into hyperspectral imaging with Telops before, you've probably seen this image. It's a great example of the kind of specificity that you get with the system and the kind of spatially resolved scene that you can get. If you have a mixture of gases within your image, you can actually separate them with the system and understand where one gas is compared to the other. So all of this can be done from quite far away. Would you say up to 5 kilometers? Of course, you need to have a good quantity of your gas, of your source, with a good thermal contrast to have a good signal reaching the instrument from that far away. You can do a detection and identification of gases for quite a few gases simultaneously. So like I mentioned here, you can spatially resolve those gases within that one frame. Some people are also even looking for aerosol measurements, but since we're talking about solid, well, more liquid particles within the air, the physics of it is a little bit different. So the Telops system don't have an integrated algorithm specifically for this. So I wanted to give an example of basically scanning through a hypercube. What does it look like when you look at this kind of data? So we have a broadband image here of a scene. It's basically the most controlled scene you might want to get, the easiest scene for a hyperspectral analysis. We have a compressed gas that's being released, that's fairly cold. And we have a black body with a perfectly controlled temperature, quite a bit warmer than the gas. So we have an optimal contrast to have the best signal possible, and as low noise as possible within your scene. So I had N2O being released in front of that black body. And if I start the video, we're basically scanning through the different wave numbers. So the slices of our data cube at different wavelength or wave number. And once we reach that area of the data, we can see that the plume gets a lot darker. So that indicates that you have those absorption peaks at those wave numbers, and the algorithm is able to identify quite easily once you have that clear signature, those clear peaks, that we have actual nitrous oxide within our scene. So that intensity of the pixels either being darker if you have absorption or brighter if you have emission are what's basically what's allowing the data to become a spectrum, so a signature of your various compounds. So this was ground. Of course, you can do that from the air, like I mentioned. We have a nice little video showing how the core system, the core moves around with the stabilization platform in the air. So you have that vibrational damping and angular movement that can happen with that platform. It's quite a light platform, so it's easy to set up into an airplane. And all of this adapts automatically depending on the operational parameters of your flight. This was installed on multiple platforms, either UAVs, helicopters, fixed-wing aircraft, and we've had amazing results. And these are the units used for the methane service that Telops offers. We've seen it excel at doing any kind of detection, whether it's day or night, if you have water, if you have snow, if it's a warm or cold day, it works just as well. This being due to the fact that we're in the long wave infrared spectrum. Now, the Hypercam Nano that we see here was not part of the product line that I mentioned earlier. That's because it's still considered an R&D project. It was a great project with amazing feats of engineering that our team accomplished over the last few years. It's still available for people if you're interested. It's important to understand that it is not a fully developed product at the moment, but it's still possible to discuss with your team about creating an R&D project for this. So the Nano is an even more miniaturized system that was developed to be implemented on drones, basically offering even more flexibility in the kind of measurements that you can do. But it still has the same powerful acquisition and detection possibilities that the other hyperspectral systems have. Sorry. So a quick glance at the kind of data that you get for those airborne systems is the same idea. For every pixel, you have that spectrum being showing if you have any kind of compound or gas leaks, or the identification of solid surfaces if you want. But you can do that over a very large area. You can basically create a mosaic of multiple data cubes over your flight path, creating a nice large image like we can see here that still contains all of that information. So the both system ground or in the air have an adjustable spectral resolution. The base information data that you get as an output are calibrated radiances, so you can immediately see the spectrum that you get in your data cube, either in radiance or in brightness temperature. Brightness temperature typically give a more direct indication of your spectrum. All of this can be done in real time with the system showing the result of the detection with a report showing the visualization quantification with the processor in the system. For solid surfaces, that's when we need that little bit of extra processing with a temperature emissivity separation that can be done with an extra software. And experts like geologists or material scientists typically have to be involved to really separate those different signatures if you have a strong mixture of different signals. So that's the kind of report that you get for the airborne, but it's very similar for the ground units just as well. So you have the detection of gases, you have your GPS if needed, timestamps, indication of altitude, latitude, and longitude, all of the information that might be required. Now to talk about the topic of today. So we'll go over the kind of improvement that we've had over the last few months for the algorithm. And Martin will take over in just a moment. I just want to mention that the improvement for that detection algorithm that does work in real time has been really impressive. So we're looking into fewer false alarms compared to the current software that's being used. We've really pushed to maintain that real-time detection and identification performances. And the key aspect was that this had to work on all systems. So the ground, airborne, and nano systems that I mentioned, that algorithm had to be possible to be implemented on all of those systems. So the key improvement factor that's measured is you are using the ROC curves. There's a few slides that Martin will go over. The receiving operating characteristic curves, either comparison of true positives and false positives. It's an interesting tool really to compare the old and the new algorithm. And the key aspect is really to look at the first 10% of that curve, see how much of an improvement and the important part of true versus false positive area. So how much of an improvement we have in that region. So I'll let Martin take over. I can hear his microphone working well.
So
there you go.
Hear me? Yes.
Yes, we can hear you. Great.
So the old algorithm that we had was based on the GLRT, so it's generalized likelihood ratio test. It's a good algorithm. It's very sensitive, and it's good to detecting spectral anomaly that correlates with a given spectrum. So if you're looking for a gas and you have some region of the spectrum that has these anomaly, it's gonna flag it. But it's sometimes non-specific. So that means that you gotta have a lot of false alarm for everything, every gas that looks similar, or even some rocks that have some special spectral feature that are similar. So the new algorithm still use the GLRT as a first pass approach. So since it's very sensitive, we use it with a low threshold to get a good candidate. So we have a lot of good pixels that are candidate for the gas that we're looking for. So we did a little improvement on that algorithm with basically the way that we select the background pixel, which are required for the algorithm, it has been improved during the project. And so when we have these candidate pixels, we group them together with the spatial connection to have a list of candidate plume. So we have identified thing that could be the plume of the gas that we're looking for. With this plume, we try to compute the background radiance for this plume. We do that with the principal component analysis of the background. And so we reconstruct the radiance that will have been behind the plume of the gas that we're looking for. So we can go to the next slide. Oh, do I have control? No, okay. And so using that background radiance, we can compute the transmittance of the candidate plume. And we can compare it to the theoretical signature that we're looking for. And we calculate a similarity test value, similarity value for that, and we threshold that value according to a variable parameter. So that's the basically outline of the new algorithm. You can go to the next slide. So I was looking at the survey, and I think that maybe I need to explain a little bit more what is a ROC curve than I anticipated. So what we do with the ROC curve is that we scan the thresholding parameters. We do detection for a data set with different parameters, and we look at how much true positive we have versus how much false positive we create. So the ideal ROC curve will be to have all of true positive and 0 false negative. So if we increase the threshold until we get some false positive, so we'll have like a box that's completely straight, that goes straight, a line that goes straight up and then stop at 1. So the integral of that ROC curve, if you look for the old integral, it would be 1. So to do the ROC curve, we have to have some annotated data. So we did some campaign. We had, I think that it was more than 10,000 hypercube. And with these 10,000 hypercube, we manually annotated the data to determine if there was gas present. Of course, we knew when we did the release, so we just looked at those data cube first. And we, for each data cube, we have a possibility of true or false positive for every gas. So with that first manual annotation, we run the test and we realized that we've missed some unintentional leak. So we had tanks that were in the field of view and they were leaking. So we had to correct our annotation for this. We also had some liquids that were evaporating for longer than we anticipated. And since the new algorithm was so good, then we realized that we have made this mistake in annotation, but then we corrected everything and we have a data set with the possibility of false and true positive. So we didn't annotate it on a pixel by pixel basis because of course it would have been way too long. So it's really on a cube by cube basis. Then we need to scan a parameter. So for the old algorithm, GRT was the probability of false alarm that was scanned to get the ROC curve. And for the new algorithm is sensitivity, is the last parameter that I talk about, the threshold at which we declare if the signature is similar enough to declare detection. So the ROC curve on the right. So as I said, the perfect ROC curve would have been a ROC curve that goes straight to 1 and then, yeah, like it's right. So the higher it is, the better. And we are interested really in the 0 to 0.1 region because an algorithm that has more than 10% false alarm is useless. Even if sometimes, like if you look at the yellow curve, it gets better than the red curve at high false alarm rate, but it's not interesting because at that point you have more than every data cube has at least one false alarm if you're looking at multiple gas. So it's really not useful. So the way that you really want to concentrate is under 10% false alarm, even smaller than that. And it's the region that is really important. So if we look at the results, the old algorithm, the GLRT, is the dotted blue line. So as you can see, if you look at the true positive rate of 0.4, we had 10% false alarm. So that's not really good. Of course, we have to put in perspective that this data set was built to challenge the algorithm. So we had multiple resolution that were not necessarily appropriate for the gas that we're looking for. We had some various background. We had rocks that has some signature. We had the common false alarm that we knew, that windshield. We had people moving. So, and we had some very small release. So we had some big release, but then we reduced the release until we couldn't see them. So it's a challenging data set. That's why the rock curve are going to be worse. For a normal data set, we have much better rock curve even for the old algorithm. But with that data set, we see that with the improved GLRT, just with the better selection of the background pixel, we significantly improve for the same false alarm rate. Let's say at 10%, we had 60% of true positive. So we detect 60% of the real leaks with a 10% false alarm rate. And with the solid line, we had the new algorithm. Since we used the GLRT in the algorithm, we had two versions with the improved GLRT and non-improved GLRT. And so the top like purple line is the final algorithm. And if you look at the integral, we have more than double the integral of that rock curve in the region. So it's a great improvement in quality. So can go to the next slide. Do you want to do this one or?
Sure, I'm happy to take over to talk about these results, those examples. So thank you very much, Martin. Very insightful and interesting to learn about those changes with the algorithm and the clear improvements with the ROC curves. So I'll go over some examples that were acquired with those measurement campaigns that Martin mentioned. So here we have some examples of that false alarm suppressions that Martin was mentioning. So with the same level of detection, the new algorithm that is at the bottom here, that's the old one, does show clear improvement. So some of the key issues that we had before were common objects. So typically car windshields were a big issue with a lot of reflection from the sky. Clothing, as well as quartz on the street, these were big issues. These do no longer generate systematic false alarms. A single gas release no longer triggers a detection of multiple unrelated gases. That was an issue as well. If you had scenarios that you had multiple gases that you wanted to detect in a scene, especially gases that can have an intersect in their IR signature, then you could create some false alarms like this. And another issues would be the movement artifact. So if you have a hand or an object moving relatively fast in your scene compared to the frame rate of the data cubes, you would have some sort of weird oscillating pattern in your image, and that would create false alarm as well due to the disruption of the interferogram during the acquisition. Now, in that first example here, so we have two of those first issues that I mentioned, so the car windshield and clothing, and we'll take a closer look. I go like this, yes. So we can see those cars showing a lot of those false alarm gases that we know are not part of the scene, but they can be part of some reflections in the background or just weird reflection absorptions that come from car windshields that we know do not contain those gases. We can see that in that whole list, we have some or quite a lot of detection in all these, and only Freon was released in this case. Madame Martin, wanted to mention.
Yeah, just want to mention that this is really a worst case. The old algorithm was better than this. We just took the worst example possible.
Yeah, pushing the limit quite a bit. Yeah. So, and you can see, so on the right with the new algorithm, it's basically a perfect detection without any of those false alarm in this case. Here's an example of that movement false alarm. So that third issue that I was mentioning. So we see that weird pattern that's created with that the broadband image. And we can see in the data, we have that slight oscillation that occurs, and that will create some false alarms in the detection algorithm. So we can see in the old algorithm, we have the detection of some of those gases with the movement, but with the new algorithm, that's taken care of. The algorithm is able to understand, basically, if a movement that is created through a movement that creates that oscillating pattern, it can understand that that is not an actual gas. It's just a movement within the scene. Now, when we're talking about multiple gases, there are a few scenarios that the algorithm can take care of. A simpler scenario is a gas emission that is very far away from one another. So you have sources that are very far away, and there's no mixture or two-dimensional mixture of the gases in your image. Then you can have multiple releases at the same time, but then there is an intersection of the gases within the image. But as long as you have some areas where you have a single gas that can be identified, the algorithm won't have any issue separating those gases and understanding that you have multiple gases in that area of the mixture. Now, where it gets difficult is when you have a source that is already a mixture of two gases, and then it's being released. So you have basically a perfect blend of two or more gases. And in that case, the algorithm doesn't have a base basically to understand that difference in signature between the unique gas, the single gas in the part of the image, and the mixture of the multiple gases. So the algorithm will have a bit of an issue in scenario C.
Yeah, detection is still possible in this case. It's just going to require a lower threshold, which is going to create maybe some more false alarms away. But
right.
This is an issue for the algorithm.
Thank you, Martin. So this is an example of ground quantification. So we had the mini CLW, and we have two releases in this case. And it does look like there's quite a bit of mixture of those gases, but there's enough pixels that separate that blue and that green gas, so in this case, acetone and methanol, that the algorithm is able to identify them quite well, even when there's a mixture, see where there's acetone, where there's methanol. And you can see in the data, it's not always clear with the naked eye that you do have those two gases, but the algorithm is able to identify them quite well. So another campaign was done combining ground and airborne systems. So that quantification campaign was basically testing the algorithm to validate the implementation of the algorithm within the software, demonstrate that real-time performance that is really key, and test the specificity of the algorithm to really see if we're getting the right gases, even when we're pushing that detection list for signatures that are very close to one another, like we can see here. There are peaks that really, they're very, very similar, and it would be understandable for a, let's say, a less performant algorithm to get false alarms with those. The campaign was done at Telops as well with those two systems, airborne and ground. We had freon, ethanol, and butanol that were released. Sadly, that N-butanol couldn't be evaporated enough to have a significant quantity of gas that could be observed with that sort of lower signal. But we had ethanol and freon that were able to be compared, and there was no creation of false alarm in that case, even though they can be very similar in terms of IR signature. And we had those other alcohols within the detection list that the algorithm was trying to detect that were very similar as well, and there was no false alarm with those. Here's an example. So we're basically running through multiple data cubes of an airborne acquisition. We can see when it's green at the top, that means it's clear. We don't have any gases. We keep scanning, data cube, data cube, data cube, and then after a little bit, then we have a red indication. That's when we have nitrile detection. And we see here we have that freon in this case, yes. And we have a very long exhaustive list of gases that the algorithm was looking for in this case as well. And we can see it's not a huge difference. It's a very small dip in the data, even with the noise of the data cube. The algorithm is able to solidly identify that freon release and not create any false alarm with all those different gases that we're seeing at the beginning. So let me just start it over to just show how many gases we had in that detection list to really push your algorithm to see if we're able to uniquely identify that freon, which it was able to do. Another example here of acetone release in this case with the ground unit. And I really love this example. It's a clear indication when we see the sort of that series of data cube of those false alarms happening with the original older algorithm with gases that are similar in terms of signature. But on the right, with the new improved algorithm, we really see that acetone is the only gas that's identified. And only that, but it's able to detect and identify the gas for a wider part of the scene compared to what we have on the left. There are more pixels that are identified. And we can see the plume moving along the multiple data cubes for a longer amount of time, longer amount of data cubes in this case. So you have a much clearer understanding of what's happening with the plume, of what is in the plume with the new algorithm compared to the older one. And lastly, this is a great example with the nano system. So these were releases of methanol in a field, and the drone basically hovering over the field, taking a multitude of data cubes. Now it's a little bit harder to see the difference because it goes quite fast. The key here would be to look at the list of, the list of gases that you have for the detection list in the software. With the original algorithm, you can see that when a gas is detected, there's quite a few of them that are flashing, quite a few pixels that are creating false positives in this case. And on the right, when we do have a detection, it is uniquely methanol that is appearing. So we have that great specificity with the new algorithm. And it works just as well with all three systems, so ground, airborne, or nano system. And as we can see, with the nano hovering quite high from the ground, it's only a few pixels sometimes, and it's able to get that clear detection only with methanol. And so we have that all covered compared to the old algorithm, really showing a great specificity and lower threshold of detection compared to before. So as closing remarks, that new DNI algorithm has really drastically improved compared to the previous one. The team has done an amazing feat of engineering, so improving the algorithm. Those false alarms on background objects or for movement artifacts are significantly less likely to occur. And that specificity of gases identification is really greatly increased compared to before. And you can reliably identify those gases in your scene with the new algorithm. Now, the computational time, some people might wonder with a new algorithm that's that powerful, does that change the processing time that it takes to do that real-time detection? And it's a new algorithm. It takes maybe a little bit more time for that DNI portion of the processing. There's more optimization that occurs during that project as well. And so all those other steps of calibration process that have been optimized will reduce the overall computational time, which means you actually are able to detect more gases in real time compared to the previous version of those systems. So overall, you get more detection in that same amount of time with a much better specificity, lower false alarm, and a better reliability for your detection. So this was the presentation of the new algorithm. Thank you very much, Martin, for your slides and your comment over the last few ones. If you have any questions, please let us know, and please visit us on our website at telops.com or the new Exosens website as well that we're transitioning to. So thank you very much. So we'll take questions. We'll stay a few minutes to take questions if you do have any. So let's start with this here. Can the thresholds be defined by users or are set at default values by your test? That's a great question. The threshold value for the sensitivity is adjustable for the user in the software. So you have great control. You have default settings as well that are indicative of like a default baseline. You can have a higher sensitivity or lower sensitivity, but you can adjust that threshold to the level that you prefer as well, depending on your tests. Another question, did you try to test the algorithm at highly mixed scenes where spectral mix may mask gases' spectral signatures?
Yeah, so if we have a mix of gases with spectral features that overlap each other, it's going to be a real challenge for the algorithm. But if they are separated spatially, they can overlap with no problem. But if they overlap spatially and they have overlap spectrally, then it can create some condition which is impossible to distinguish. Of course, reducing the threshold will make you detect these gas, but reducing the threshold will also increase the false alarm rate. One mitigation possible, if you have mixes of gas that are spectrally overlapping and you know the right ratio of these gas, you can create a custom signature, because with our system you can not only detect gas with a pre-existing library that we publish, you can also create your own signature. And if you create a custom signature, which is the mix of the two gas that you're looking for, then you can detect it with your new algorithm with no problem.
Good point. Let's see here. The question for the oil and gas application. The leaks are well-mixed methane plus a full suite of volatile organic compounds. Will you struggle to differentiate or have additional false positives? That's a great question for a methane team. Martin, I know you work with them as well. Do you have any comment on that?
Yeah, so mainly in the oil and gas, the gas I know is present is ethane, which does not overlap with methane, so shouldn't be a problem to detect. If there's other gas, they're usually either non-visible in the long wave band or have insignificant signature, like H2S is not significant enough. It's never enough to create problems. So basically, when you try to detect a natural gas leak, only looking at methane is the way to go. And I'm not an oil and gas expert. If you have some specific gas that you are wondering, could answer this question if I knew the gas, but from what I saw, we never had a problem with natural gas. So
great, thank you.
Follow up to that question.
Let's see, we'll give them a bit more time, see if they want to write a follow-up question. In the meantime, let's see other questions up there. How often do you reckon that recalibration needs to take place? That's always an interesting question. It depends on where you take the measurement, the atmospheric conditions, depends on the spectral resolution as well, depends on your parameters of acquisition, and how rapidly that calibration might change depending on all of those parameters and the atmospheric conditions. Don't know, Martin, if you have a specific recommendation, but that I know it depends on each measurement campaign.
Well, we're talking about what kind of calibration. It could mean a lot of things. I'm not sure.
Okay,
I can actually read the questions, unfortunately, but the system is calibrated with internal black bodies, and that only changes when the system change temperature. So if we have a system that is open for 1 hour, there's almost no need to do more calibration for a ground system which is stable in temperature. For a nano system that maybe goes into different air layers, it could change. So it's really the temperature of the instruments that determine the radiometric calibration requirements. Depends on the application, but it's usually not a great downtime. It's very small, and we usually have no problem placing that calibration outside interesting measurements. For the system, there's other calibration for the system, but these are all factory calibrated and don't need to be done again for the life of the instrument. So again, if I could read the question, maybe I'll have a different answer.
Yeah, it does literally say, how often do you reckon that recalibration needs to take place? The newer upcoming systems will have a different way they're calibrated, and it will be done with that more permanent calibration at Telops. So that's going to be a different method of operating. So you don't need to recalibrate in the field, basically, with those newer systems. Let's see. So we have quite a few left, but we'll take maybe one more. How do you characterize your hyperspectral camera? Like geometric corrections and calibration. I guess that's related to the other one that we talked about, the recalibration.
So we have a calibration for the spectral accuracy, and we use either water bands, so that we know where the water bands should be theoretically, and we calibrate the system on those bands. So either by looking at the sky or at the black body with just ambient humidity, and so we adjust the laser wavelength tells us with an FTS, it tells us what our metrology precision, and with that we calibrate if there's like a little uncertainty in the laser wavelength. Well, then we can calibrate it using those water bands. So we have a very high precision on spectral accuracy, and it's stable for the whole system. Now, I think that you're talking also about what we call the off-axis effect, so that each pixel is going to see a different OPD. So then it will see a different wave number grid, and that's also characterized in the same way with those water band. And so we determine the FOV of the system and its central axis, and then we can completely correct to have water bands that are very precise for all pixels.
All right, great. Well, I think we'll leave it to this. Thank you very much, everyone, for attending. If you've registered, then you'll receive the list of questions with answers after you get a recording of the webinar as well. So thank you very much. I hope you all have a great day. And thank you again, Martin, for participating to this webinar. Have a good one.